This is Chief LAN Cables. Welcome to the Data Communications and Internet Protocols. In this module, we are going to look at how data is transmitted from one point to another, how really it goes. So, in this module, we are going to focus on the things like the internet protocols, and we look at the data communication principles. For example, if we come here, we can see that under the data communication principles, there are certain things that we have. For example, the telegraph codes. These include the Morse code. Then we have got the AES CII code. Then we have got the EBCDIC code. Then we have got the Unicode. So if you look, the Morse code is a system of communication that use dash and dots and dashes to relay messages. A dot looks like a period, and a dash is a long horizontal line. A dot is called a dit, and a dash is called a da. So it's all about the dits and das. If you look, this is how the Morse code looks. This picture clearly shows how the Morse code looks like. So if you can see from here, this is where in telegraph communication systems, this is where we can find some encodings about the codes which are related to something like, for example, beep sounds. When you are pressing the telephone buttons, it will say, like, say do 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 do, right? Those are the codes dzinenge dzakaitwa this Morse code. Then we have another encoding system inonzi American Standard Code for Information Interchange, which is ASCII. This represents data in 7 bits. It's a 7-bit character set, right? So which means if you look, A is translated into 100001 in base 2, which is equals to 65 in base 10. Then the small letter A is 110001 in base 2 is equals to 97 in base 10. So this is how it is. This is how the American Standard Code for Information Interchange works. Then if you move on, you are likely to see this is part of the ASCII. You can go, and the picture is not that clear, but if you go on 65, you can see A. 66, you can see B. But if you look at these binary formats of these characters, you can see they are 7 bits, 7 bits and stuff. So this is how the this encoding system was made. Then we have got this guy who's called EBCDIC. EBCDIC meaning extended binary coded decimal interchange code. This data encoding system was developed by IBM, and it is mostly used on its computers that uses a unique 8-bit binary code. So this is a 8-bit character set encoding system. So instead of using 7-bit as the American Standard Code for Information Interchange does, this one now inoshandisa 8 bits, right? So these are the telegraph code that we have. So tikabva ipapo, we can now see kuti we are now getting into the most interesting topics, where we are looking the broadband versus baseband. We should know, in most cases, people be just hearing broadband or baseband, but they don't really know what it is. So this is when we are going to look at it Like here, we can see the difference between broadband and baseband. Then a baseband network is the one in which the cable or other network media can only carry a single signal at one time. It means that only one signal can be carried at a time. In this case, transmission medium, may be it copper, fiber, or whatever other medium, only uh, a single signal will be carried at a time. But we have got a broadband network, on the other hand, can carry multiple signals. A broadband network mu cable munogona kupfuura nemasignals akawanda at the same time, using the discrete part of cables bandwidth for each signal. As an example of a broadband network, consider the cable television service you probably have in your home. I think most of us have come across a situation yekuona bora, especially the Premier League, English Premier League, and most ladies like to watch Z World. We can watch ZBC, we can watch BBC, Al Jazeera, and so forth and so forth. Those signals are multiple signals that are being carried in a single wire, and as they are carried in a single wire, we are likely to see the moment you select your favorite channel, inobva yatobuditsira zviri kuenderana nezvawachuza, which means kuti the signal is there, but you select kuti uri kuda papi, which means when the signal is encoded into the transmission medium, ndo panoshanda multiplexing. The signals are multiplexed and then transmitted over the network cable. Then when they reach the destination, they are demultiplexed so that anyone can easily select zvaari kuda kunzwa. The same way, let's say we need to send a call from Harare to Gweru. Yeah, there are people in Gweru and our calls are coming from Harare. What really happens is, kana tichishandisa broadband network, we can actually take calls ese ari kubva muHarare, signals ese emuHarare, then we put them in the transmission medium, we multiplex. Then when they get to Gweru, we demultiplex, so that each and individual person ari kufanira kunzwa call yake anonzwa call yake at that time. That's how broadband network works. I think I've explained a clear example and a good example. Then we have got my transmission modes. These transmission modes, and this is how data is being transmitted. So we have the two major types, which is serial and parallel. And as you can see, the serial transmission mode is subcategorized into synchronous and asynchronous. So if we move on from this, we can now see, all right, there's this thing that we call the parallel. What happens? The parallel transmission model, or the parallel transmission mode, it has several channels between the sender and the receiver. It is used to transmit data over short distances. Each bit takes its own channel, its dedicated that is its own dedicated channel. So what happens ndezvekuti zviri kuitika panhingirikini parallel transmission mode tiri kuona isusu paine machannels akawanda, but it's only suitable for shorter distances because it is too expensive, number one. Then number two, ikada kuita longer distance pamwe panogona kuita possibility yeana electromagnetic interference, ana mutual induction, which means tinoita kuzotowana distortion of the actual signal redu rinogona kuita distorted rikatosvika kwariri kuenda radhakwa. That's why we use it for shorter distances. So advantage, it's fast mode of transmission, since signals edu anenge achifamba in parallel, so it's very fast. Then disadvantages, we have reduced bandwidth due to mutual inductance, covers only short distance to avoid distortion, clock skew, costly to implement. Obvious, these multiple channels that we'll be enjoying, they come at a price. You have to know it's very expensive. Then possibility of interference. Then we look at the serial. There's only one wire to connect the sender and the receiver. All the bits move in one channel, one bit after another. Starts with the least significant bit to the most significant bit. What happens is for the folks who have grown up in the rural areas, kuti I really anticipate that kuti maiti mukaenda kudhibhi, mombe dzese hadzingopindi mudhibhi mukahwani, munopinda one at a time, one at a time, one dong at a time. That's what we call serial data transmission mode, right? You say one bit at a time, right? Transfer mabits akawanda at the same time, right? That's what happens by serial transmission model. Then tirikuti isusu, that serial is subdivided into synchronous and asynchronous. So the asynchronous send a bit stream with no common clock between a sender and a receiver, which means kuti kana iri asynchronous, iyo serial iri asynchronous, the example yandingangotore kana tichiti there is no common clock, I think kuti pari kutaurwa frequency. The receiver and the sender can actually operate at different frequency levels. Let's say the sender is operating at the sender is broadcasting at 50 hertz or what megahertz or whatever, then the receiver ari kana pa 25 hertz kana 25 megahertz, whatever. That's how it is. There's no common clock between the sender and the receiver. Let's say a practical example yatinayo here in Harare, we can say tikenda ku National FM, be it Radio Zimbabwe, National FM, or whatever other radio station, we can see kuti they are operating at a certain frequency. But if you go to Chimanimani, if you go to Honde Valley, if you go to Chipinge, they have got different frequencies dzavanobata nadzo radio. This is how asynchronous is serial transmission. Then if we go for synchronous, the synchronous now requires a buffer storage for at the two ends of the line. The sender and receiver operate at the same clock frequency, right? Which means kuti kana sender ari pa 50 hertz, that's it, nekuna receiver 50 hertz. So we have got my data circuits, we have a 2-wired circuit, we have got a 4-wired circuit, which means you need to know those and understand. Then this is the other story. This is the beginning of the story. Once you don't know this thing, then you are actually lost. This is what we call the OSI model, which means this OSI model was developed by ISO, right? This model is very important. It's a 7-layered model. Yatinoona kuti ine the application, presentation layer, session layer, transport layer, network layer, and the data link layer. Then finally at the bottom tine yatiri isusu are the physical layer. So this OSI model is very important because it helps us to understand how data is packaged, how data is transmitted, what really happens, and the likes of protocols anenge achishanda along the way patinenge tichida kutransmita data redu. And the OSI model, as I said, was created by the ISO. Then it stands for Open Systems Interconnection Model. Open Systems Interconnection Model. That's what it means. So these layers are very important. These layers are very important, and there are certain protocols that are found by each layer. For example, on the application layer, we can find protocols like the HTTP, HTTPS and stuff like that, and the list goes on like that. Then we have got the presentation layer, the session layer, the transport layer, the network layer, the data link layer, and physical layer. So what I can say is data communication and IP begins with the OSI model. If we go on, if we are to come here, we can see now we have the other important model, which is called the TCP/IP model. This one is contrarily, on the other hand, is different. It's slightly different from the OSI model. This one in a about the four layers instead of the 7 layers, but the protocols are almost similar, and as it is, we'll look at it as we go. But it is very important to know that one, the TCP/IP model, right? Then TCAP Vipapo, we can now see the 7 layers of the 7 layers of the OSI model. We've got the application layer, which provides access to the network for applications. This is where we can find things like application programming interfaces and stuff. The application programming interfaces are meant for us to share data and stuff like that. Then we have got what we call the presentation layer, which translates data from the format used by applications into one that can be transmitted across the network. Because when data is being transmitted, it is in another format that cannot even understood by the applications. It handles encryption and decryption. That is one of the functions. Encryption, then we can have decryption. It also provides data compression and decompression functionality. Formats data from the application layer into format that can be sent over the network. Right. That's what the presentation layer does. Then we have got the session layer, which synchronize the data exchange between applications on several separate devices. The session layer is responsible for managing and controlling the synchronization of data between applications on 2 devices. It does by establishing, maintaining, and breaking the sessions, right? So that's what we get from the session layer. Then we have got the transport layer. This one is the most important, but it doesn't work in isolation of the others. It is dependent on other layers. So provides connection services between the sending and receiving devices and ensures reliable data delivery, manages flow control through buffering or windowing, provides segmentation. This is one of the most important thing that the transport layer does, which is the segmentation, then error checking, then and the service identification. The basic function of the transport layer is to provide mechanism to transport data between network devices. It provides the mechanism in which data is transmitted. So primarily it does this in 3 ways. Error checking protocols, a transport layer ensures that data is sent or received correctly. This is where patinoona wana TCP/IP vachizotiitira vana 3-way handshake then and stuff. Then tinoona kuti isusu service addressing protocols such as TCP/IP support many network services. The transport layer makes sure that the data is passed to the right service at the upper layers of the OSI model. Segmentation. To traverse the network, blocks of data need to be broken down. It breaks down the blocks of data into packets that are manageable, that are of a manageable size for the lower layers to handle. This process is called segmentation. This is the responsibility of what? Of the transport layer. So what we basically saying is, for data to be handled by the lower layers, the transport layer itachi segment, or it breaks down large data blocks into smaller packets which can be easily handled, which are easily manageable, right? We have got the protocols that operates at this transport layer, and the 2 major protocols are the TCP/IP and the UDP, which is user datagram protocol, right? So the TCP/IP is connection oriented, which means kuti inoestablisha yatinoti 3-way handshake. yekuti panofanira kusendwa ma-acknowledgements ekuti packet rasvika here kana kuti harina, but the UDP is connectionless, which means kuti if once the packet is sent, it doesn't confirm whether have it reached its destination, was it correct or whatever, it just send like that. Okay, fine. Then we now look at the network layer, which is the important. This is where routing takes place, which means a router is a layer 3 device, a layer 3 network device, which means it handles the discovery of destination system and addressing, provide the mechanism by which data can be passed from one network to another. This is where networking takes place, and the device that is responsible for internetworking in the router, the primary responsibility of the network layer is routing, providing mechanism by which data can be passed from one network system to another. It does not specify how the data is passed, but rather provide the mechanism to do so. Functionality at this network layer is provided through protocols, which are software components, right? So that's how the network layer works. This is where routing is performed. But at the data link layer, this is where switching takes place, because the switch usually make use of MAC addresses and stuff. So this is where we can say the data link layer is responsible for getting data to the physical layer so that it can be transmitted over the network. The data link layer is also responsible for error detection, error correction. This is where wana humming code, wana CRC patine tichizowashandisa kuita error detection, error correction, and hardware addressing. The term frame is used to describe the logical grouping of data. The logical grouping of data is a frame in this case. Yatinoti kana kuti protocol data unit in this case inenge iri frame, right? So if we move on, we can see kuti isusu the data link layer has two distinct sublayers: the media access control MAC sublayer and the logical link control sublayer. So those are the most important layers that should be known at the data link layer. So from there we can see we have got the physical layer. This is where we can see the raw bits being transmitted over the network, where the raw bits are converted into signals, sinus. In this case, we can see our raw bits being, or our digital waves being converted into sinusoidal, electrical waves, waveform. I don't know what to say about these signals, but they will be in sinusoidal format. Then they will be transmitted over the wires or whatever transmission media. This layer have got the direct connection. Do you need direct connection, hardware connection, be to the wires and stuff? The physical layer of the OSI model identifies the physical characteristics of the network, including the following specifications. We have got the hardware, the type of media used on the network, such as type of cable, type of connectors. We have got the connectors like my RJ45 and stuff, and pin out format for cables. We've got the topologies that can be used there, be it bus, ring, whatever. Common topologies including ring, mesh, star, and bus. In addition to this, the physical layer also defines the voltage used on a given media and the frequency at which the signals that carry data move from one state to another. So it determines the frequency yacho change kamera say bit, megahertz, whatever, and it. Then kana tapedza kudaro, then we can now safely look at the transmission mediums. These are the very, very important things we should know and understand. We should know things like twisted pair, the coaxial, then the fiber optic. Those are the most important transmission modules. The transmission mediums, right? Tiri kutarisa isusu kuti data redu rinenge richifamba mumhepo here, kana kuti mumawires, kana kuti fiber and stuff. Then tikatarisa panapa, this is how the twisted pair looks like, and the twisted pair cable is subdivided into UTP and STP. As you can see, this have got the STP, which means shielded twisted pair, which means this is the shield and it is outside. It is the wires are inside. Then the UTP and shielded twisted pair are in a cable or are in a shield, but this one is shielded. This one is not, is unshielded. That's the difference now, which means the twisted pair is good for outdoor purposes, but this one may be needed for indoors, right? Then if you look, the two main types of twisted pair cabling are in use today: unshielded twisted pair and shielded twisted pair. The UTP is significantly more commonplace than STP and used for most networks. Shielded twisted pair is used in environments in which greater resistance to EMI and attenuation is required. The greater resistance comes at a price, however. So which means the shielded twisted pair now inoda kuya kwekuti patinetida greater resistance to electromagnetic interference, and of course the panenge pachiitika attenuation. Attenuation simply means the degradation of the signal as we go. Because sometimes the signal have got the tendency rekuda kuzodzikira power, so which means kuti unotozoona kuti madecibel ako akuda kudhakwa dhakwa paya. So the greater the resistance, resistance iyoyo the greater the resistance comes at a price, which means kuti kana iri shielded inokwanisa kuresista zvinhu zvakaita sana attenuation and EMI and it. Then the additional shielding plus the need to ground that shield, which requires special connectors, can significantly add to the cost of a cable installation of STP. Yeah, my special connectors in the need to ground that shield and stuff zvinodhura saka, which means in other words tingoti STP inodhura but yakasimba. Then this is how this is the other diagram for our STP. Iri kutiratidza the shield, then twisted pairs, then the protective jacket. We have the protective jacket, the outer jacket, and the shield inenge yakashirika pano, then doma twisted pair acho. I think this diagram is very clear and vivid. So from here we can now look at the UTP, unshielded twisted pair cable, a higher category, which means this one ine nhau dzayo dzoda kunzwisa, dzoda kuti munhu wenetworking aziye. Beyond this specification, the TIA or EIA T568 standard defined levels of performance. This UTP inema levels of performance that are referred to as my categories. That's why you can see Cat 5, Cat 6, Cat 7 and stuff. A higher category rating means that a cable is more efficient and able to transmit data at greater speeds. The major difference between the different cable categories is the tightness of each wire pairs twisting, commonly referred to as twist per inch. Saka the difference now chinodiffaringa macategories inyaya yematwist per inch. Imwe inokwanisa kunge ine matwist akawanda per inch, imwe ine mashoma pachi per inch, right? So that twisting ine zvainoaffecta panyaya dzeperformance. So we can now look at the following table. If you look this table, you can actually see the maximum frequency for each category. As you can see, we have got the category 1, Cat 1, Cat 3, Cat 5, Cat 5E, Cat 6, Cat 6A, Cat 7, Cat 7A. And these are the common name: fast Ethernet, gigabit, Ethernet 10 gigabit, and see. And these are the speeds for each category. And we have got the maximum length support, which is 100 meters, 100 meters, 50 meters, 100 meters, and it goes on like that. Then the network application, we have got the 10 base T, where we are saying 10 baseband, right? Twisted pair, 100 base T, 1 gigabit base T, Then we have got frequency 0 megahertz, 16 megahertz, 100 megahertz and stuff. Those are the speeds my maximum frequencies. So baseband, I think tamboitaura kuti it's one after another. So these are how these transmission cables really works like. So if you look at here, panenge pachinzikana kuti 10 base chakuti the base refers to the fact that the network uses baseband transmissions. As explained, a baseband network is one in which the network medium carries only one signal at a time, as opposed to a broadband network which can carry many signals simultaneously. All of the Ethernet variants are baseband except for one broadband version, which is rarely, if ever, used. The T in 10 base T specifies the type of medium the network uses. For example, T in 100 base T stands for twisted pair cable, right? So from there we can safely proceed to see this another cable yatina inonzi the coaxial cable. Coaxial cable yeda inaumbooma. We have got the conductor pakati, we have got the braided metal inenge protector. This is the dielectric insulator. Then we have got the outer cover. This is how a coaxial cable looks like. And coaxial cable or coax is commonly referred to as being around for a long time. It found success in both TV signal transmission as well as in network implementation. Coax is constructed with a copper core at the center that carries the signal, plastic insulation, braided metal shielding, and an outer plastic covering. Coaxial cable is constructed in this way to add resistance to attenuation. This one, resistor attenuation, which is the loss of signal strength as it travels over a long distance. Crosstalk, the degradation of a signal caused by EMI and stuff, or caused by signals from other cables running close to it and EMI. Resistors zvese the signal are degraded because of those shieldings that dzakaitiswa. Then this is the fiber. Fiber in this strength fibers cladding, then the optical core. This is where ichi chiri pakati ichi ndo chinenge chichitransmita data racho in form of light. Then we've got this outer jacket. So the fiber inenge ine two types dzatinoti isusu single mode and multi mode, and we are saying the fiber optic cable consists of a core made of glass. The other thing about the fiber optic is the very fast light, the data is being transmitted in the form of light, and obey the Snell's law. Snell's law yekubenda kunoita light through a medium. If you go back and refer that Snell's law, you can understand the better how a fiber optic really work. Pane pachiitika reflection of light, so that reflection inongoramba ichibounza zvichitoenda signal richitofamba. There are two main types of fiber optic called the single mode and multi mode that differ in several ways. They have got the difference, and single mode is typically rated 8.35 out of 125 8.3 out of 125 microns, and multi-mode fiber at 62.5 to slash 125 microns. This measurements refer to the thickness of the core and the thickness of the cladding and the core together. Light travels down the relatively thin core of a single mode cable without reflecting off the cladding as much as in multi-mode fiber thicker core. The signal is carried by single mode. The signal carried by a single mode cable is generated by a laser and consists of only a single wavelength, while multi-mode signals are generated by the LED. This is where the difference is. We should know how signals anenge achigeneratwa sei, be it per single mode and per multi mode, right? And the single mode is usually suitable for a longer distance. So now we need to look at the network topologies that we have. I think this It's like more of poetry. This is more of poetry that anyone can sing these network topologies. The arrangement is here where we can see we have got the bus topology, we have got the star topology, we have got the ring topology, then we have got the star bus, then we've got hierarchical star or the extended star. But basically what I'm saying is if you look at the ring topology, most people think the computers are being connected in a big circle. That's not a ring. This is not a physical ring, it's a logical ring in which that the signal is being transmitted in a circular fashion. It's not being transmitted in the way we can think isusu teichifungidzira kuti ichatransmitwa ring rakatodai. No, it's the logical implementation. It's really logical. It's not something we can touch kuti ndatione ziring so and it. Then we have got vana bus inenge ine terminals anenge akaiswa kuma ends uku to avoid nyaya signal bounds. Then the star inenge ine central device pakati, right? So atinoti hybrid networks. Then in network design, you may be asked to design a network for a particular organization. So the first thing you can pick up my topologies or you can pick up my network devices. As we have explained the OSI module, you now know the router is the network layer device, and we have got the switch, which is a layer 2 device. So you pick up layer 2 and layer 3 devices. Then you can pick up my cablings, the right cables uchashandisa. You can pick up my connectors, you can pick up what I can say, topology ndataura nezvayo. There's a lot of things, my protocols, even the protocols, right? The software, my firewalls. I think the list is endless. So nema quantities, you specify my quantities, uda ma switch mangani, uda ma router mangani, uda chi and it. Then you combine, then you justify the implementation, right? If you come here, you can now see the connectors that we have. We have got the RJ45. This is very perfect. This is nice, as you can see, and I think most of us have used the RJ45. We also have the RJ11. Then we have got these fiber connectors, the ST connector, the SC, the LC, MT, RJ. These are some of the fiber connectors, right? These RJ45s are used for the Ethernet. These ones are used for the fiber. Okay, so tichibva pama connectors, you should know my LAN protocols. This is the food for thought. Everyone should start cracking his or his head kumbofunga my LAN protocols. And think, instead of today I challenge you, instead of continually think your girlfriend, start to think LAN protocols. If you think more of LAN protocols, you won't even be a victim of Mujolo pandemic. Thank you. Okay, let me proceed now. We have got to look at the media access methods. This is where we see kuti banana ma bus topologies edu ring topology. Tinana ring topology ndo inoshandisa chi token passing. Then we've got SYSMA CA, which stands for carrier sense multiple access with collision avoidance. Then imwe yacho carrier sense multiple access with collision detection. What happens there kuti token passing ndo the media access method inoshanda the ring topology. Iyo SYSMA CA, we are saying kuti inogara yato avoida the ningirikini, inocheka kuti muningirikini medu mu transmission media medu muri say yogara ya avoid. Then iyi inodetecta collision. Pakaitika collision, inobva detecta kuti something wrong. Then computers anenge acollide anobva amboiswa back of phase. But in a collision avoidance inotanga yatocheka traffic. Kana mine traffic aitosend to avoid unnecessary drama. Okay, fine. Then from here, we can now look at the network devices. We have got router, switch, bridge, hub, wireless access point, repeater, firewall. Those are very important. As you can see now, these are the network devices that we have. Those are the network devices that we have. Tinayo switch yedu, tinaro router redu, tinaro hub redu. Then we've got this wireless item, wireless access point. I don't know this stuff. I think most of us have managed to see these things physically with our naked eyes, right? From there, all we need is to get more and more about these ones. We should know, we should familiarize, and we should know the vendors. These routers and stuff, they are being manufactured by the giants like Huawei, Cisco and stuff, and there's this other giant, the Alcatel is very good manufacturer of these devices. And I've forgotten another very important vendor of these things. Then we have got now we now need to look at error detection and correction. The most important thing about this thing is to understand the exclusive OR gate. I think we have done, if you put my inputs 1 and 0 in an OR gate, what do we get? Let's say A, you have got the column which reads 0101, then B 0011, then X 0110. So if you put 0 na 0 pa exclusive OR gate, you get a 0. If you put 1 and 0, you get a 1. 0 and 1, you get a 1. 1 and 1, you get a 0. That's how the exclusive OR gate operates, right? So from here now, we need to see, okay, how does we use this exclusive OR gate Pachi per error correction, error detection? Well, we have got this guy what the cyclic redundant check. Cyclic redundant check ndo patiri kuti isusu we have MX, which is the message to be transmitted, and the polynomial key, which is also known as GX, right? So which means this key is, let's say the message to be transmitted is 101,000 and 1101. Then here the polynomial key is 110101. So which means the message we need to transmit is MX plus CRC, right? So see the following example. The example is here. Yatapa iyo yekuti generating key yedu which is the polynomial key na message yedu. We only do the long division. So what we simply do is we just bring here 110101 here. Before we go on panapa, what do we look? We look at the polynomial key and we count how many bits do we have. We have 1, 2, 3, 4, 5, 6. So we just subtract 1 bit to that, and there are 5 más zeros kumberi kuno. These are the 5 zeros that we are seeing at the front of MX. Then we start division, and the division goes on. So which means this one only detects an error, but it doesn't correct the error. Which means if we put this CRC yatinoitaona panapa tikaisa pamazeros up, if the message is error free, we can get a 0 remainder. But if the message can any errors, then we get a remainder and got weird and strange. So it doesn't really correct, it just detects an error. It's an error detection mechanism. So what happens is you just bring here the generating key here, then you perform exclusive OR gate. 1 and 1 you get a 0, then 0 and 1 you get a 1, 0 and 1 you get a 1, 0 and 1 1, 0 and 0 you get a 0, 0 and 1 1. Then we are left with how many bits? 1 2 3 4 5. We need to make them 6. We drop 1, then we bring back here. We perform the exclusive OR gate. 1 and 1 0, 1 and 1 0, 1 and 0 1, 0 and 1 1, 1 and 0 1, 1 and 1 0. Then we are having how many bits? 4. So then we have to drop down the next 2 bits here. Then we bring back here. Then we perform exclusive OR gate. We repeat the same process till we get to find our CRC as 0110. 01110, right? Something like that. Then if you understand this concept, then you're home and dry. haunetseki and hautambure. Then we are coming now to the Hamming code. We have the message which is m is equals to 100111011. Masteps atina tinoshanda neformula inonzi calculate the number of redundant bits by 2 to the power r greater than or m plus r plus 1. M, which is the number of bits of the message that we need to transmit, then r, which is the borrowed bits, then 1 is a constant. So we determine then if you calculate that, the next thing is to determine the Hamming code length by m plus r, then determine the positions of redundant bit, then use exclusive OR gate to calculate the values of redundant bit atinenge takalabhela kuti r1, r2, r3, r4. So if we come here, you can see kuti we have got 2 to the power 4. Because why? Because in this case we have got 8 bits, but we need to do 2 to the power something which is greater than 8 plus 4 plus 1. So 2 to the power 4, which is 16, greater than or equal to 13, which is true. Then which means kuti Hamming code is m plus r, which is m8 plus 4, which is equals to 12. So we subdivide, tinobva tacreata tumagroup twedu 4 tobva talabhera tichibva uku tichidzokera uku, then we fit in the message yedu ishi into the remaining boxes. So we shared all the powers of 2. For example, 2 to the power 0 is equals to what? 2 to the power 0 is equals to 1. Then 2 to the power 1 to 2. Then 2 squared. 2 squared is 4. 2 to the power 3 and 8. So we shared. So the next thing we have to find R1, R2, R3, R4. Right. What we do now is we come here. Then we change. We now look at my numbers ese anema ones like 12 pana 1, pana 12 pana 1, pana 9 pana 1, pana 7 pana 1, pana 5 pana 1, pana 3 pana 1. So we list those numbers in descending order tichidzika like this as shown in the table. You look my 12 here, my 9 here, my 7, 5, 3. Then we can now convert these numbers to binary. If we convert them to binary as shown, then the next thing we perform the exclusive OR gate tichidzika. This is where you say 1 na 1 you get a 0, and 0 na 0 0, 0 na 0 0. Then panapa tinenge tatolabhera kuti r1, r2, r3, r4 and it. Then 1 na 0 ndi 1, 1 na 1 0, 0 na 1 1, 1 na 0 1. Then we get the final one here. Then panapa 0 na 0 0, 0 na 1 1, 1 na 0 1. Then 1 na 1 0, 0 na 0 0. Then tichienda takadaro. Then afterwards you can easily come back. Kanaona r1, r2, r3, r4. You can now come here back. Then you can actually fill these things, and you can see with no swap tendeka, and there's not tendeka for sure. Zvinoendeka. I needed to modify this table, but it was something crazy. Yeah, as you can see, this is r1, r2, r3, r4. Then tatongo filler here. So from here now we need to discuss something about data recovery. Data redu sometimes, let's say masevers atsva kana kuti paitika an accident, paitika floods, we always need to provide a data recovery mechanism. This is when they came up with the redundant array of inexpensive disks. A RAID array is a group of hard drive that function together in any one of various ways called levels. These levels, there are 6 basic RAID levels numbered from 0 to 5, plus several other RAID standards that are proprietary or variations on one of the other levels. The different RAID levels provide varying degrees of data protection and performance enhancements. So we have got RAID 0 yatinoti disk stripping. As you can see, this is the 0 RAIDing. Then we have got RAID 1, the disk mirroring and duplexing, right? We are just providing the mirrors. A, B, C, D anenge aine mirror rake, E, F, G, H ane mirror rake, each and every disk ine mirror yaro, which means kuti zvanyorwa kunoku zvinononyorwawo nekumira. So more RAIDs. This is RAID 2 harming ECC, RAID 3 parallel transfer with shared parity, and the list goes on like that. So you have to understand this RAID, these RAIDs, right? Then after that, we have got the functions of operating system. We have to understand the basic. What is the operating system? How does an operating system boost? This is where we look at things like memory management, file management, process management, and input-output management. Those are some of the functions of operating systems. Then we have got the thing is we also have my types of operating systems, my distributed, my network operating, real-time there are lots of them. But now we also have to understand my examples atagara tina. For example, Macintosh by Apple, Windows by Microsoft, Unix, and so forth. Then Linux is another example of an operating system, right? From there now, we need to look at the internet infrastructure. This is where the internet protocols will actually come into play. What is an internet infrastructure? The internet infrastructure is an array. It's an array of remote hardware and software working to send and receive information to various systems. Every instant of a page loading on a computer's web browser, a really simple syndication feed streaming into a reader, RSS, or a voice over internet protocol VoIP call being made represent this complex internet infrastructure. Its basic components, the basic components of internet infrastructure include my data centers and networks, my servers, my storage devices, and server applications. The hardware may be localized in specific countries, but the network infrastructure spans international boundaries to make the internet a worldwide phenomenon available in any region that is a functioning localized network. So I think kuti this is the IP header, the structure of our IP header. Let me try to zoom it out so that we can actually see how it is. Maybe if I do this one, everyone could see kuti zviri kuitika panapa. Yeah, I think it's clear. Everyone can see clearly. Yeah, you can now see clearly. This is the IP header. Yakagurwa. You should know kuti an IP address is something which is 32 bit long. If you look, they are saying 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. These are the 4 octets. Each octet have got 8 bits. So 8 by 4, you can actually get 32. So we have got the IP version, which is maybe it could be version 4 or version 6, whatever. Then we have got the IHL type of service. Then we've got identification, then flags, total length, fragment, offset, header, checksum, protocol, time to live, TTL. Then source IP address, destination, options, data. So this is the information that we can find in an IP header, and which is very important for us. Then we have got the TCP IP model. Yatataura isusu kuti about the 4 layers: application layer, transport layer, internet layer, then the network access layer. Then we now look my IP classes and subnetting. What is subnetting? We are just breaking down the IP address into the subunits, or we are using a block of an IP address. We are just subdividing it into subnetworks. As you can see, this is my IP address. But of course, inenge ine the network side and the host side. But when we are using the classical addressing system, we can actually have class A, class B, class C. This is how it looks like. Kuti the class A inenge one part network, then 3 parts host side. Then class B in a network 2 parts network, then 2 parts host. Then class C in a 3 parts network and 1 part host. And it saka I think ndo zvingoripo panapa. Maadresses emclass A anotanga na 0 chaku 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 or 1 to 126 decimal. Class B addresses begins with 10 chaku chaku tichienda takadaro. As you can see, you can actually define when you see an IP address, you can simply say this is a class A or class B, or this is a private or a public internet protocol address, right? Anyways, we can now see this is how it is. The same this illustration is just showing how do we go about when we are doing with the classical subnetting. Subnetting is all about breaking down the IP address into subnetworks, something like that, nothing more. And it, but now they discovered the classical subnetting waste ma resources. This is when VLSM subnetting was introduced. The VLSM subnetting, which means variable length subnet mask. So we have the approach that we use, to net this a set of rules, which means it can attribute us a network address when we need to find out the network address of a particular subnetwork. Tinongoti all zeros host portion. Then first host, we can only say all zeros host portion and 1 for least significant bit. Then last host is all ones host portion and 1 for least significant bit. This one is all ones for host portion and 1 for least significant bit. Pakatika typing error. Then we've got the broadcast address inongoti all ones host portion, and it then subnet mask is vice versa. It says all ones network side and all zeros host portion. I think if you understand these fundamentals rules, then variable length subnetting mask would be very easier. Most guys are good at convincing ladies, but when it comes to subnetting, they are very down. I don't know why. It's because they fail to understand these rules and it. So that's how it is. Kana kunopfimba musikana kuri easy. Subnetting is much easier. Itori much easier than kupfimba musikana. Kupfimba musikana kwakaoma stereki. Subnetting is very easy, right? So okay, well, if you look, this is an example. Variable length subnet mask example. We have given that IP address, then this /26 na ndo inotibatsira kudivide kuziva kuti the network side ndeipi, the host side. Then from there we can simply find out the first host address, network address, last host broadcast address, then subnet mask. Then as you can see now, you can actually see kuti panapo we've already subnetted. The first thing is like we convert the last groups into binary. So from here we can count 26 bits: 8, 16, 24, 25, 26. Then we shade this one accordingly. Tichishandisa malows kuti tautoziva kuti from this line tautoziva kuti this is the host side, this is the network side, and the network address kuti tiwane inoti all zeros host side, then inoti all zeros host side and 1 least significant bit and stuff zvichienda zvakadaro. The moment we convert this tofana kubva tamaisawo kudecimal, then subnet mask haichatinetsi inoti all ones host side, then all zeros network side. If you just do this, then it is smart, right? So from here we can actually see good now we have the last thing yatoda kutaura the TCP/IP model. This is our TCP/IP model. As you can see, ndo pane protocols edu, application layer ine HTTP, DNS, domain name service, SMTP, SNMP, Telnet, FTP, POP, those ones. Transmission transport layer ine UDP, TCP, internet layer ine IP version 4, IP version 6, ICMP version 4, ICMP version 6. Then the network access layer in a frame relay, SYSMA CD, triple P, Ethernet. Then those are the functions. The function of application layer represents data to the user plus encoding and dialog control. Then transport layer supports communication between diverse devices across diverse networks. Then determine the best path through the network, that is the internet layer. The hardware layer, which is the network access layer, which controls the hardware devices and media that make up the network. I think from there you can be safe to look at the transport layer protocols, which is the transport transmission control protocol and the user datagram. The first is connection oriented and the later is connectionless, meaning that the TCP provides reliability and error-free delivery of data. Saka the TCP is more reliable as compared to UDP. UDP is usually used to send control data, including voice and other streaming data, where speed is more important than retransmitting. Where speed though, saka each and every protocol ine advantages ayo nema disadvantages. Let's say you are creating a chat app, paunoda kuziva kuti message yasvika here, yazosvika yakakwana here, maybe use TCP, but kana wada kuitawo mavideo calls woshandisa UDP. Okay, this one, TCP and UDP. The TCP protocol receives packet from the internet layer, reorder the packets correctly since the packets may arrive out of order, evaluate the data in the packet and send an acknowledgement signal to the sender. The sender will resend the packet if no acknowledgement signal is received. Packets need to be resent if the original packet was corrupted or did not arrive at the destination. For this reason, TCP is called a reliable protocol, where UDP is unreliable because it doesn't reorder packets or send an acknowledgement signal to the sender. When UDP is used, it is the responsibility of the application to reorder packets. So that's what I had for you, and these are the last notes dzandinadzo panapa. Toda kutarisa chinhu chinonzi the domain name system. Most guys, they hear some folks say domain inotengwa .com, .net, .go, .org, whatever. Computers are designed to work with numbers, while humans are more comfortable working with words. This fundamental dichotomy is the reason why the domain name system DNS came to be. So we can look how we are kwakaita internet. Computers, it really is kutango communicate using my IP address, but it's only my computers and understand my numbers. We as humans, we cannot easily remember my numbers. For example, www.com, www.google.com, it's an IP address expressed in word format. The word format is friendly to the human, but the computers really understands my IP address. So the domain name system yakauya kuzobridge the gap between the user and the computer. So the function of the DNS service is to resolve host names such as server1.xy.com, tail1.co.zw, tail1online.chak. Such a resolution system makes it possible for people to remember the names of and refer to frequently used hosts. Using the easy to remember host names than the hard to remember IP addresses. So this is how the DNS structure look like. This is the DNS tree, like domain name system inenge ichizoita mapping zedu. So as you see, pamunovhista mawebsites enyu, this is the tree-like structure of the domain what. So we look now, the picture is clear now. I've actually expanded it. So as you can see, there is a root here. Then we've got the network and its children. Then we have got the com and its children. Then we have got the org and its children. These are examples of my domain names and ones which undiscovered: www.facebook.com, www.chapchap.net, then www for my non-profit organizations, then anenge ari ma-subdomains, and these are ones are the hosts and it. So tikauya panapa, we can now look at the same thing. Tine website redu rinenge richinzikana kuti www.corp. Let me expand this so that you can clearly see the hierarchy. And we have got the DNS name like www.mycorp.com reflect the system's place in the domain hierarchy. We have got the root here. We have got the domain name. Then we have got now this one, vanodi yanisa panapa mycorp auya panapa, which means kuti mycorp wacho anenge ainewo achild zvichingoenda zvakadaro .com, mycorp, www mycorp.com. This is the hierarchy. This is the order of our domain name system. Then I think kuti oh, sorry guys, I have to cancel this alarm. Okay, fine, thank you. So ndasvika kwekupedzisira now. Kwandasvika ndokumapena. After this domain name system, tinoda kunzwisisa nyaya dzema-application layer protocols at this TCP IP model. These are hypertext transfer protocol and how they works. Moving files between devices. We have got the file transfer protocol, moves file between devices. We have got the simple network management protocol, the telnet simple mail transfer protocol. That's what I had for you. And of course, we need to understand the VoIP, the voice over internet protocol, how it works. We have got the examples like Skype and stuff. Even WhatsApp can do video calls. This is another example of VoIP. I don't know. Then you can go through it. And it's a method of taking analog audio signals, like kind of you hear when you talk on the phone, and turning them into digital data that can be transmitted over the internet. VoIP can turn a standard internet connection into a way to place free phone calls, whatever. So after that, this is the table which is really showing how we can troubleshoot the internet problems. We have got trace route, we have got the ping, we have got the ARP, netstart, nbstart, IP config, if config, depending machine yako, and notaura mapurposes atinozvishandisa. So I am very thankful. I think I've managed to go through this. Thank you for listening. This is Chiefland Cables. We are engineered. We are very happy. And I think I'm looking forward to expand technology, to introduce new technologies to the world. I've managed to come up with technologies that have never been there. And it's an obvious case that I'm going to learn them in one of the days. Thank you very much. I wish all the best. And this one, I hope you find it very useful, resourceful, very pleasant, attractive. And I hope you are going to digest this data and you're gonna make it. Thank you very much. Thank you, guys. This is Chiefland Cables, the pioneer of technology. One mpana anorema masters a technology. Thank you. Bye bye.